In lecture 2, mainly we will discuss how we can expand the full adder to implement a parallel binary adder and what's the addition process and one practical IC which is used for this parallel addition is 74LS283. We'll also discuss 7483 also, and how we can expand the 4-bit adder to implement 8-bit or 16-bit or higher than that. And next topics are very important. They're called ripple carry adder and look ahead carry adder. And first we will discuss difference between these two, and we'll discuss the advantage of look ahead carry adder, and finally the circuit to perform a look ahead carry operation. Okay, so we'll start from a very basic thing. How we can add two binary bits numbers. For example, the first number is 1 1 and second number is 0 1. And if you add these two numbers, okay, if you use a full adder, for example, this is a full adder, and if you use a full adder, there will be three inputs A, B, and a carry in. Okay, and there will be two output, sum output and carry out. Okay, so this is a full adder. So we can see how we can implement a full adder to solve this particular problem. Okay, here the first two bits are 1 1. There is no carry in, so we can assume that the C in is equal to 0 in the first case or first column. So if you add 1 plus 1, you will get 0 sum and carry is equal to 1. So this is a carry out of the first case. So here it is 1 1 and 0 in the first case, and here it is 1 and the carry out sum is equal to 0 and carry is equal to 1. When you consider the second column, again we need another addition operation, so we can use another half adder. So in that particular full adder, here the two inputs A and B 1 1 and the previous carry, okay, that is 1, so we can consider this as a carry in, and here the sum is equal to, we can see that 1 plus 1, if you add 1 0 and plus 0 will be 0, so sum is again 0, but the C out is equal to 1, so this is a C out. Okay, and this is the sum of the second full adder. And so in order to implement more than 1 bit or more than 2 bit or 3 bit, 4 bit, etc., we can cascade, we can configure this full adder or more than one full adder to perform this particular operation. Okay, we can see one circuit which perform this particular operation. We already indicated two individual full adders. Now we can see the combined effect. So this is the first, for example, the first bit is A1 and second one is A2. The first number, let it be number A, and this is the second number B, B1, B2, the 2 bits as given in the example. And here you can see 3 bits, S1, S2 and S3. Okay, so this S3 is the carry out of the last full adder. So if you add the first two cases, you can see full adder and the carry in is equal to 0, so you will get a S1, that's LSB. This is the carry of the first case, so here it is indicated as okay, the 1. And now we can use the second full adder, and the output of the first full adder, that is the C out, is connected to the carry in of the second. So you can see in this particular example, so this particular bit, okay, is shown here. C out is connected to the C in, and this is a second full adder, and second full adder, this will be S2, and this carry out we can consider as the S3. So this is the MSB bit and this is the LSB bit. Okay, so in this way you can connect the full adder to implement the parallel binary addition. So this is for two binary digits with 2 bits. Now we can see how we can use this full adder to implement 4-bit parallel addition. So here you can see that in this particular example, C0 is given 0. Okay, so here C0 is equal to 0, and A1, A2, A3, A4. This is the first number A, which is given 0, 0, 1, 1. and the second number B1, B2, B3, B4 is given 0, 0, 1, 1. Okay, now we can see how this particular circuit will operate. And in the first case, this is a full adder. So this is the first full adder 1, and this full adder will provide an output S1 is equal to 0 because all the bits are 0 and carry in is also 0. So the first carry out, so here it is indicated as C1, C1 will be 0, and this 0 is connected to the second full adder, input of the second full adder. And for the second full adder, again you can see that it's 0, 0, 0. So the S2 bit is also 0, and here the C2 bit also 0 because there is no one input, all the values are 0. So from the two table we know that carry sum is equal to 0 and carry is equal to 0. So this C2 is connected to the input of this third full adder. So here it will be 0, and now we can see that A3, B3 inputs are 1, 1. So if you add 1 plus 1 plus 0, so that will be the input for the full adder. So you will get sum is equal to 0, so S3 bit is equal to 0, and this carry bit is equal to 1. And this carry is propagated to the next stage, that's the last stage, and here the input will be 1, and now we can see how it will operate. So here it is 1 plus 1 plus 1. So here the sum is equal to 1 and the carry output will be 1. So this is the final output. So you can write like this. So final output will be 1, 1, 0, 0, 0. So if you are adding 4 bit and finally you are getting 5 bit, including this carry. So this is the operation of a 4 bit parallel adder, and you can see how we are connected each full adder, okay, to implement a 4 bit parallel adder. And one more thing, in this particular case, when you add two 4 bit number, here we are using a full adder in the first stage, but this is not compulsory that we need to use a full adder in the first stage. We can use a half adder also, because in the first stage there is no carry in. Normally the carry in is equal to 0 in most of the case. So instead of the first full adder, I can replace with a half adder also. Okay. So when you implement a 4 bit parallel adder, I need 3 full adders and 1 half adder. So this combination also works in the similar way, because in the first stage there is no carry. Okay. Now we can see a circuit which perform the 4 bit parallel addition. So in the previous case, we can see that we are using 4 full adder circuits or 4 full adder ICs. Now we are using a single IC. Okay, it can perform the 4 bit parallel addition. So if you take this particular IC, it required different pins. So the first one is 74283, and another IC I can introduce is 7483. So both can perform the same operation, but the pin outs are different. So 74283 is more common because the VCC and ground connection is similar to your logic gates. Okay, 8 will be the ground and VCC is 60. That's one of the main difference between this 7483 and 74283. Okay, and here you can see that this particular IC, if you look at this A1 B1 2 bits, okay, and here you can see some output of the first 2 bits. Okay, there is a Z0, that is a carry in of the first stage, and here you can see that A2 B2, okay, and this will be S2, and here you can see that B3 A3 inputs, and here you can S3 output. Similarly A4 B4 and the sum S4 here, and finally the carry out. Okay, carry out the final stage. So we can add 2 binary values, each 4 bit wide. Okay, and you can also take the output S1 S2 S3 S4 and the carry out C4. So this is the logical symbol of the 7483. But if you look at this particular IC, here you can see that this is VCC and this is ground. Okay, And here also you can see that A1, B1, S1. Okay, and Cin will be here. Okay, and here it is A2, B2, S2, and here it is A3, B3, S3, and here A4, and pin number 16 is B4, and finally S4, and this is a carryout. So if you compare these two IC, you can see that the 7428 is more convenient to connect, okay, because 2 bits positions are close to each other. But here the VCC also at 5 and ground is stop. Okay, that's only difference we can at this particular moment we can see. This pin diagrams are different for 74LS283 and 7480. Now we'll see how we can use this 7483 to implement, or a 4-bit adder, how we can use this single 4-bit adder IC to perform an 8-bit. So in order to perform an 8-bit addition, 8-bit parallel addition, we need to use two 4-bit adders. Okay, so this is the first 4-bit adder. It can be 7483 or 74283. So this is the first stage. Okay, this is the stage 1. Here you can see that 4-bit A1, A2, A3, A4. Here it is B1, B2, B3, B4. So here you can see the remaining bits A5, A6, A7, A8, and here you can see that B5, B6, B7, B8. So you can see two 8-bit number. Okay, A8 to A1 will be one number, which is A, and another number B, which is BA to B1. And we are using a 4-bit parallel adder to implement 8-bit addition. So you can see that this is the logic that we are using. The output of the first carry out of the first IC is connected to the carry in of the second stage. So in this way you can expand this 8-bit 4-bit adder to 8-bit adder. Here you will get S1 to S4, S3, S2, etc. Here also you will get S5, S6, S7, S8, and this is the carry out. So this will be the MSB, and this will be the LSB, least significant bit. In the first stage there is no carry, so we can connect this C0 to ground. Now we can see another circuit. A similar idea we are using to implement a 16-bit adder. Okay, this is a 16-bit adder circuit. 16-bit adder circuit. For that we need 4 4-bit adders. Okay, so this is the first stage. This is the stage 1. We'll take first 4-bit. So this is the second stage, and this is the third, and this is the fourth stage. Okay. Here also you can see the same logic is used. The first stage carry out is connected to the input of the second stage, and the carry out of the second stage connected to the carry in of the third stage, and carry out of the third stage is connected to the carry in of the fourth stage. So here you can see that this is the MSB part and this is the LSB part. Okay. Similarly, you can implement 32-bit or 64-bit any number by using a 4-bit adder. Now we'll move to the more important topic, that is known as a ripple carry versus look ahead carry adder. So there are, if you consider any parallel adder, there are two types of concept, adder concept, adding concept, or they are known as ripple carry adder and carry look ahead adder. So the main difference between this ripple carry adder and look ahead carry adder is that the speed of operation is very important. The speed of operation is very low in the case of ripple carry adder, but look ahead carry is much faster than ripple carry adder. So when you do the practical circuit or in implementation of microcontrollers or in ALUs, we will mainly use the look ahead carry adder, but there is another problem, the circuit will be more complex. Okay, so at present we will only focus on how we can improve the speed of an addition operation by using this look ahead carry adder. So before explaining the look ahead carry adder, I will just give you introduce the problem that we face in ripple carry adder. So here you can see one example. For example, the ripple carry adder in which the carry output of each full stage connect to the carry input of the next stage. We already explained a similar circuit. Now we can see that in this particular circuit, Uh, the inputs are 1 1 1 1 0 0 0 0. Okay, a1 a2 etc. And the carry z0 is equal to 1. Okay, let me see 1. Now we can start the explanation. Here in this particular case, the first full adder, the inputs are 0 0 and carry in is equal to 1. Okay, and after addition process, okay, uh, 0 0 and 1, so you'll get sum is equal to 1 and carry is equal to 0. Okay, and this carry will be propagated and it will reach at this particular point. Okay, second stage. So here we will get 0, and here you can see that the second stage the inputs are again 0 0 and the carry input is 0. So the sum is equal to 0 and carry is equal to 0. Now this carry is moved to the next stage and here it becomes 0. Okay, and now we can see there are two inputs, 1 1 and the carry input is 0. So 1 plus 1 0 and the carry out is equal to 1. Okay, so if we move to the final stage, this one will reach to the carry node of the last stage, and if you look at this particular stage, there are 3 ones, so MSB will 1 and carry out will be 1. Now we'll discuss what's the problem in this particular circuit. See, for the second stage, that is FA2, so FA2 want to calculate the sum by using the inputs, let be A2 B2. Okay, and it's also required the carry in from the previous stage. So assume that the all inputs are available at the same time. Okay, so when you apply the inputs, A1 to A4 and B1 to B4 available at the same time, but you can see that in this particular case the Cin should reach at this particular point only after completing the addition of the first stage. Means if you use any digital circuit in order to perform, let it be a full adder. So for example, this is A, B and C. Assume that it takes some time to evaluate the result, and finally the result will be available only after a few seconds or few nanoseconds. So that delay is actually, we will call it as a propagation delay or something like that. Okay, so after this propagation delay, it will reach at the output of this full adder. For example, we are concentrating on carry. So assume that the carry out we will get only after 8 nanoseconds. Okay, so when you apply some input at the 0 seconds, only after 8 nanosecond the C out will be available. So initially we are applying a 1 at the particular input and 0 0, but the C out is available only after 8 nanoseconds. Okay, so before that 8 nanosecond the input of the second stage is available, but in order to get a proper output we need the carry out of the first stage. Then only I can calculate the carry out and sum of the second stage. So for that we need to wait 8 nanosecond. So only after that 8 nanosecond, the carry input of the first stage will be available on the second stage. Now again we need to wait an 8 nanosecond to generate the C out. Okay, because again this circuit required some time to calculate the C out. So again we need to wait 8 nanosecond. This 8 nanosecond is a typical value. It can be 10 nanosecond, 6 nanosecond based on the circuit. So as a total, in order to get a proper C out in the second stage, we need to wait 8 plus 8, total 16 nanoseconds. Similarly, after this 16 nanosecond, the C out will be ready. So this C out will be available to the input of the third flip-flop, that is FA3. So only after 16 nanosecond. Again after 8 nanoseconds, so C out of the third full adder is available. Okay, so assume that the fourth stage inputs are available at 0 time itself, but this C out of the third stage is available only after 16 plus 8, 24 nanoseconds. Okay, after 24 nanoseconds time, this carry out or 1 will be available at the scene, and after performing the operation, the C out of the fourth stage will be available again after 8 nanoseconds. So total 32 nanoseconds. So if you take 8 in each stage, and the worst case, you need to wait up to 32 nanoseconds to get a proper output at the last stage. So this is the problem of ripple carry adder. And I assume that if the number of bits is 8 or 16 or 32, we need to take again more time. So this is one of the problem that faces in the ripple carry adder. Okay, this is a waste case delay that we are discussing. Anyway, in order to solve this particular thing, we are using another circuit that is known as the look ahead carry adder. Okay, we already discussed what's the problem of ripple carry adder. It causes some time delay in addition process, carry propagation delay for each full adder. Okay, that's a main problem. We already discussed all these points. Now we'll move to the look ahead carry adder. This is one of the method to speeding up the addition process by eliminating ripple carry propagation delay. So in look ahead carry adder, we are actually predicting, we will predict the output carry, or we are anticipating the output carry of each stage by using its inputs. Okay, so this is a concept behind look ahead carry. Instead of waiting for the previous stages, previous n-1 stages, we are just calculating the carry, or we are predicting the carry by using some other concept. So for that, we are actually using two terms, carry generation and carry propagation. Okay, so here you can see the truth table of full adder. So A, B, C in will be the inputs. So the three inputs, and this is the C out. Now we are discussing only about the C out. Okay, and one more thing, in each case, the C out is calculated based on A, B, C in. But in ripple carry adder, we will wait for this C in. That's the main issue that we are facing. So in order to avoid that, by eliminating the C in, we will predict the C out only by using A and B. Okay. So that's the concept behind look ahead carry. By using A, B inputs, we will predict the C out. If you know A, B, C in, definitely you can calculate C out by using full adder concept. But in look ahead carry adder, we are calculating or we are predicting the C out value by using the inputs A, B. So now we can analyze this particular truth table. So if you look at this truth table up to this point, okay, 0, 0, 0, 0, 0, 1, 0, 1, 0, there is no carry out. So we don't want to consider about that. Now we can see the 0, 1, 1 stage. So if you consider this particular stage, A, B inputs will be 0, 1. At that time, output is 1. Okay. And again, in 1, 0, there is no carry out. So we don't want to consider. Carry out is equal to 1 in this particular case. So this is one case we need to consider. Another case, you can see that 1, 0, A, B will be 1, 0. So there also the carry out is equal to 1. Why we call it as a propagate means, so C in is directly propagate to output side. So here you can see in that the inputs are either A or B is equal to 1. Here also this input A or B is equal to 1. So carry will be propagated. So here you can see the carry propagation occurs when the input carry is rippled to become the output carry. The input carry may be propagated to the full adder when either or both of the inputs are 1. So now we consider either A or B is equal to 1. Now we'll case another two cases. So if you look at the last two cases, okay, last two cases, here you can see both inputs are 1, 1. If both inputs are 1, 1, the output carry is equal to 1. So the last two stages we can call it as a carry generation. So the carry generation occurs when output carry is produced internally by the full adder, or carry is generated when both inputs are 1. Okay. Now we can reduce or we can implement a circuit which produce output 1 when both A and B is equal to 1. So I can call that carry generation process as GI. Okay, so that variable I can define as GI. That is, the last two cases we can define like this: when both A and B inputs are 1 1, the output is equal to 1. So that is simply the AND gate, AI and BI. So GI, carry generation at the ith stage, can be implemented by using AI and BI. So we don't want to bother about the Cin of the previous stage. Okay, that's the advantage. And the carry propagation, so here also you can see that this 1 is propagated to the output side. So either you can consider this 1 1, the last stage in carry generation or in carry propagation. That's why it's written as carry generate or carry propagate. Now we need another logic for this carry propagate, because this 1 is propagated to here also this 1 is propagated. So for that you can see that either A or B is equal to 1. Make it, if A is equal to 1 or B is equal to 1, the output is equal to 1. So this can be implemented by either by using an XOR logic or by using an OR logic. So mainly in most of the textbooks they are following this A XOR B combination. It's not compulsory that we need to use A XOR B combination. We can also use A plus B combination also to generate carry propagate. So carry propagate is indicated by PI. So PI can be written as AI XOR BI. In ith stage, the carry propagate logic can be implemented by AI and PI. Now we can see how we can use this to find the carry. So now we defined the two terms, carry generation and carry propagation. Carry generation is simply defined by this equation: GI is equal to AI BI, and the carry propagation concept is implemented by PI is equal to AI XOR BI. It can also be implemented by using A or B, but we will follow this XOR concept in this particular lecture. Okay. And I already explained that by using K-map also I can conclude that carry generate and propagate logic. So you already indicated the previous, this is the same two table we defined in the previous slide. So here from this particular example you can see that this logic, carry generate logic, is indicated and grouped here. So this is simply you can write AB. So that's why we indicated carry generation logic G is equal to AB, and this logic is carry propagate. So if you write the truth table for this particular carry propagate, sorry, Boolean expression for this, you can see that scene can occur, okay, when, if you look at these two group. So here you can write it's B is common for both the case. Here you can see that this is A is common, and now here it is seen. Okay, now here it is again seen, and so that is C in B plus C in A. Okay, so this is the propagation logic. So C in will be propagated when this group. Okay, leave it. This is a group that which indicating when C in will propagate. Okay, so this is the logic. A bar B is 1 when A B is 1. Then A B bar is equal to 1. Okay, this is the logic where C in is operating. So now we'll move to the logic part. So now we'll explain the circuit part. So this is a full adder circuit, full adder using two half adders. So in this particular half adder, you can indicate that PI is AI XOR BI. So here you can see that this is an XOR gate. So PI can be written as AI XOR BI. Okay. Now similarly GI you can define in the first half order, that is AI into BI. Okay. So this is the logic to implement PI and GI. So if you take a full adder using two half adders, so you can easily define PI and GI. Now by using this PI and GI, you can define SI. That's a sum output. So this is the first XOR output, that is PI, and another input is CI. So if you CI and this PI is XORing, so you'll get PI XOR CI. And in the lower case, you can see that this input, one input is CI, another input is PI. Okay, here it is PI. So this input will be PI into CI, and this carry out of the full adder can be defined as PI CI plus carry from the previous stage, that is indicated as GI. So these are the two output equation. So sum and carry we can calculate by using this particular formula. And now we can see the expanded form. So we can write the carry of each stage. So here the carry in of the first stage, that is C0. If you take any parallel adder, the first carry in is equal to C0. That is the input carry. So we will get it from the input side. And now we can write the carry out or C1 of the first stage. So if you take any full adder circuit, circuit will be like this. This is a C0, and this is the first stage A0, B0, and sorry, A1, B1, and this is C1, and this is A2, this is B2, and here you can see that carry input of the second stage. Okay, carry input. Sorry, carry input. In this way we are connecting. So this C1 we can calculate by using G0 plus P0 plus P0 into C0. So this is the general equation for calculating Ci plus 1. So C1 we can calculate by putting I is equal to 0 here. So G0, P0 and C0. And similarly, the next carry C2. Okay, I can calculate the next carry. I can calculate like this, C2. So I can put 1, I is equal to 1. So it becomes G1 plus P1 and C1. And if you expand this particular thing, G0, I can calculate G0 is equal to A0, B0. Okay, so this is A0, B0 plus P0 can be calculated from this formula, A0 XOR B0. So A0 XOR B0 into the rest C0. Okay. Similarly, if you write the second equation, C2 G1 P1 C1, this G1 I can write by using letter G1. I can write A1 B1. So here you can write A1 B1, and second one C1. C1 I can substitute here. Okay. So now it will be G0 plus P0 C0, and you can substitute all these values from the previous case. From this we can see that C2 only depends on A0, B0, and here if you look at A1, B1, P1 is A1 XOR B1, and G0 also depends on A0, B0, and the other term also. So all these terms, if you expand like this, all these terms depends only on the input and only one carry, that is C0. So it will not wait for the previous carry C1, C2, etc. So that's why look at array perform faster when compared to other circuits. So similarly, you can write C4, C5, etc. So just expand this particular equation and substitute the A, B values. So if you expand the equation, you can see that it depends only on the input values and not on the previous carry. It only depends on the first carry, okay, that is available from the input side. So no other carry is used to calculate. When you calculate the carry, we are not using the previous stages. So we don't want to wait for the previous carry. That's the concept. So here you can see that from that particular equation, you can implement the circuit. Okay, G0, for example, uh, C1. Okay, C1 you can calculate by using G0, and here you can see that this is P0 is one input, another input is C0. So P0, C0, and C1 can be implemented G0 plus P0, C0. In the similar way, you can calculate the other values also. Okay. Now, when you implement the circuit level, the final circuit of look ahead carry adder look like this. So we need a look ahead carry generator module. So that is already we explained. So this thing we need to implement, and so this particular block shows the previous diagram, but in this case we are using a 4-bit. So we need a extra one more stage to calculate that, and here you can see that Z0, A0, B0, A1, B1, A2, B2, A3, B3. Okay, and the output of each stage depends on P0, P1, P2, P3. This C1, C2, C3, C4 will be available by using the look ahead carry loss, the prediction loss. Okay, so if you look at this particular circuit, in order to calculate C1, C2, C3, we don't want to wait an equal amount of time. For example, the circuits actually contain two stages. So this is stage 1 and this is stage 2. Okay, in stage 1 we are using only AND gate, in stage 2 we are using only OR gate. In order to calculate C1, again the signal will pass through an AND gate and OR gate. So for example, this AND gate provides a delay of maybe 4 seconds, and this OR gate also provide a delay of 4 seconds. So 4 plus 4, after 8 nanosecond, okay, 8 nanosecond delay we will get the output. Similarly, if you calculate C2, again it requires a 4 nanosecond in this particular stage, again a 4 nanosecond in this OR gate stage. So total 8 nanosecond. Again here also it's 4 nanosecond, here also it's 4 nanosecond. So total 8 nanosecond we require to calculate C3. So, but in the case of ripple carry adder, it's different. In order to calculate C3, we need to get C1, again C2, and then only we can calculate C3. So we need to wait more time to calculate higher carry bits. Okay, that's the difference between ripple carry adder and look ahead carry adder. So this is a final block diagram which shows the entire module which is implemented by using look ahead carry adder or a faster adding circuit.